Let's talk about the complex ion formation. What is a complex ion? A complex ion containing a central metal ion, metal cation, I would say Mn plus, and then it is bound to one or more molecules or ions. So in most of the cases, the central ion is a transition metal ion because transition metal ion is having vacant orbital. They have vacant orbitals, so they can occupy or they can the surrounding molecules or ions can be occupied by the empty orbitals on this the empty d orbitals on the transition metal ions. As an example, if we look at this cobalt chloride, which is initially a pink solution, and that will turn to blue with the in the presence of the uh, water molecules. Right. So this is the formation of that the complex metal ion. The tetra chloro cobalt 2 plus is a the complex metal ion, metal complex. Right. So we can write a formation constant for this, the formation of this complex metal ion, the complex of the metal ions. So how do we write these the formation constant? That is described in the next slide. And if this formation constant is a higher value means the stability of the complex ion is also great. If the K is a larger value, that means the stability of the complex ion is great. Here you will see some of the formation constants listed for the formation of these complexes. How do we write the metal ion complex? Right. So we'll get the form, formation constant is abbreviated as F subscripted K. So we take the concentration of the product, the concentration of the complex in the numerator, and that is divided by the concentration of the metal ion and the concentration of the other ions or the metals. So in a formation constant is the forward reaction should be written as the as formation of the complex, and always in the formation constant you have the concentration of the complex in the numerator, and the concentrations of the reactants, the concentration of the reactants will be multiplied in the denominator. uh, if again if the kf is large mean the complex is very stable. Let's see how we can solve a problem with the complex ion formation. Right. So we consider the formation of this complex. But here is the equilibrium constant we are given. So this is actually the opposite or the deformation of the complex ion. So we get it that's the equilibrium constant that which is actually the reciprocal of the formation constant. So when you see that the equilibrium constant for this deformation, look at this figure. It is 10 to the negative 15. So this K is very small. Then we can assume the X, the amount that would be dissolution or dissociate is very, very small, and that's a insignificant number. That will be an insignificant amount. Right. So the problem said the concentration of ammonia was 3.0 molar. That will be actually diminished by 4 times 0.01, which the uh, because the we need the that 4 times of this. The stoichiometry between copper and ammonia is 1 to 4. So we need 4 times 0.1 to make this the complex. Right. So therefore the concentration now because it was started as zero point 0.1 and 3.0. So this is the limiting reagent. So that will be entirely consumed to make this copper complex. And it was taken zero point 0.1 times 4 from ammonia to make 0.10 complex. Now we have 0.10 concentration concentrated complex. Then we consider uh, the dissociation because we need to find the free copper 2 plus ions. So then we construct this the ice table, and it is will be minus x and plus 4x for the change in concentration, and equilibrium concentration will be 0.010 minus x for the complex, x for copper 2 plus ammonia, that would be 2.6 plus 4 times x. So when I solve that, and I get the x as this. So this is the amount of free copper that or the copper 2 plus remain in the solution. So it is a very small value. So the uncomplexed copper 2 plus is extremely a small value. Practice problem 6. In the presence of aqueous cyanide, cadmium 2 forms the complex ion uh, cad, uh, tetracyano-cadmium 2 plus. Determine the molar concentration of free or the uncomplex cadmium 2 plus ions in the solution when 0.20 moles of 0.20 moles of cadmium nitrate is dissolved in a liter of 2.0 molar sodium cyanide ion. Right. So we are given the formation constant for the cadmium complex as 7.1 times 10 to the 10 to the 30 10 to the let me see 10 to the 16. Right. Um, But we now need to find the free cadmium 2 plus ions in the solution. Therefore, we should consider the dissociation of this complex. Right. So therefore we need the reciprocal of that the formation constant. So the reciprocal of the formation constant is 1.4 times 10 to the negative 17. So that is actually for that the equilibrium constant. So when we write the equilibrium constant, we write the opposite of the formation constant. So now you have the concentrations of the dissociated ions in the numerator, and the concentration of the complex is in the denominator. Right. So that is actually equal to the 1.4 times 10 to the negative 17. Now, we need to find the concentration of the remaining one because the stoichiometry between cadmium and cyanide is 1 to 4. So the uh, this was started with the sodium cyanide was added like 2.0 molar. But what is the concentration of the cadmium 2 plus now? Yes, zero point 0.2 moles, and there is 1 liter. So what is the concentration of the cadmium 2 plus? Yes, cadmium 2 plus concentration is 0.2 moles divided by 1 liter, so that is 0.2 molar. So what is the limiting reagent? Yes, the cadmium. Therefore, the 4 times of the 0.2 moles will be consumed from the cyanide to form the complex first. So the initial concentration for the complex is 0.2 molar. This the cadmium was entirely consumed, therefore the initial concentration is taken as 0 for cadmium 2 plus, and the cyanides will be 1.2. Now we consider the equilibrium, the change minus x plus x, and plus 4x will be for the cyanide concentration, change in concentration for cyanide ions. So equilibrium concentrations for the complex will be 0.20 minus x, x for cadmium 2 plus, and 1.2 plus 4x will be the cyanide ion concentration. So then you will plug these values into the equilibrium constant, that is 1.4 times 10 to the negative 17 equals x plus the 1.2 plus 4x fourth divided by the zero point 0.2 minus x. So this will be considered as the, so I would say this, the we going to uh, we have to um solve a quadratic equation. So I just wanted to, I don't want to scare you all of that you have to solve this type of mathematical operation. No, you don't need to worry about that. I would not give you that hard mathematical operation to solve in the exam. But I just wanted to go through the procedure. That's how you can calculate the free cadmium concentration, that is the X. So you solve this equation and you will find the X. The X would be the uncomplex cadmium 2 plus concentration.